Hello everyone, welcome back to the F equals MA Club. This is the online lecture for day 7 in which we talked about gravitation. I know a lot of you couldn't make it and it's alright, just make sure to watch the entirety of this video. So let's get straight into it. Just a little bit of review. Last time we talked about moment of inertia, which is how hard it is for an object to rotate. It's the rotational analog of mass. We talked about the two main theorems for moment of inertia, which are parallel axis theorem and perpendicular axis theorem. We talked about the other rotational analogs, which are angular momentum, and especially conservation of angular momentum, which is even going to be used for this lesson. And we also talked about rotational kinetic energy. Finally, we also talked about rolling, where we talked about rolling without slipping, where there must be friction, but friction does not do work. And we also talked about rolling with slipping, where our angular speed is going to be greater than our linear velocity times our radius. Alright, so there's going to be two parts of gravitation that we're going to be talking about. One part is Newton's laws, and one part is Kepler's laws. So let's first talk about Newton's laws. So Newton's laws, we have Newton's universal law of gravitation, which is that every particle attracts every other particle in the universe. And we have a very important equation for gravitational force, which is F equals our gravitational constant times our two masses. So in this case, it could be mass 1 could be our Earth, mass 2 could be our moon, and divided by our radius squared, and radius is the distance between these two. So G is the gravitational constant. This equals 6.67 or around 6.67 times 10 to the negative 11, and this these dimensions, they don't really matter. It's just important to remember that number. Remember that this is a conservative force, so it has a radial nature, and angular momentum is conserved, right? And remember this r squared. This is going to be really important since gravitational force is directly proportional to 1 over r squared. Alright, so some extensions on gravitation. We have our potential energy, and this is just going by the formula, if you remember from the first day, which is that our potential energy is equal to the negative derivative of our force, right? So for this case, our force is gmm over r squared, and we can say it's dr. In this case, that means that we can derive this to make it equal to the potential energy given here, which is negative gmm over r, right? All right, let's keep on going then. That was just a little demonstration. We have our acceleration, which is gm over r squared. And on Earth, that turns out to be around 9.81 meters per second squared. But for the competition, remember that we're only using 10 meters per second squared, right? The big thing about this is that our acceleration is not dependent on our object, on our smaller object or our satellite. It's dependent on the central body. Velocities, we have orbital velocity and escape velocity. I won't prove these here. If you do want to see a full proof, please feel free to search this up online. Our orbital velocity, we see that it's square root of gm over r, and our escape velocity is square root of 2gm over r, and this is based on kinetic energy, sorry. But the big thing about this as well is that, remember, it's not dependent on the smaller mass, it's dependent on the central body's mass. So in this equation, the only part of the satellite that would actually matter is this extra height. The mass of the satellite won't change its orbital or escape velocity. Alright, so the total energy in orbits, right? So we have circular orbits and elliptical orbits, and I might just prove this if I have the time to do so. So, remember that our total mechanical energy is going to be equal to our kinetic energy plus our potential energy, right? And so in this case, our potential energy is, as stated before, negative gmm over r squared, over r, sorry. And so that's going to make this equation equal to 1 over 2 mv squared minus g little m big M over r, right? So we can actually say that gmm over r squared is equal to mv squared over r. And this is because if we look at our previous equation for our orbital velocity, right? And since this is in a circular orbit, it has an orbital velocity of square root of gm over r, right? So that means that mv squared is going to give us gmm divided by r times r from here. So that gives us r squared on the bottom. So that's why these two are equivalent. And I'm just going to erase that right now. And so that means that our k is going to be 1 over 2 times the absolute value of our kinetic energy. And we can also say that our total mechanical energy is going to be the negative of our kinetic energy, right? So if our total energy, say, increases by 15 joules, right? Then our total kinetic energy will decrease by 15 joules. So that's what this is about. So next part, we have our elliptical orbits, and these are based on the conservation of angular momentum, right? So that entire L squared over 2I, remember that L is our angular momentum, and the 2I on the bottom, remember that our L squared is going to be IW, and so this is basically just saying this L squared over 2I, if we just think about it for 2 seconds, we realize that this is just equal to 1 over 2 times I omega squared, right? Because L squared, I squared, omega squared divided by I, yeah. Okay, so basically almost the exact same equation. Remember that our energy is equal to our kinetic plus our potential, and this is going to be equal to our L squared over 2I, which is basically this minus GMM over R, right? And so the interesting way that we can go about this is now we can say from here we can derive that our energy is equal to negative GMM over 2A. And there's a huge proof for doing this. It basically banks on the fact that our moment of inertia, remember our moment of inertia is equal to mr squared, right? And it kind of just banks off of that. If you want to see a full proof, you can just let me know, or you can just search it up. But this equation that I just showed you, this negative GMM over 2A, this is something that's really nice to keep in your mind. Some problems actually do require this. Just a little other thing that I forgot to mention. The gravitation unit isn't really tested too much. It was tested a lot more in past years, and it's been tested a little bit more in recent years, as in like around 2 questions per test. But it's just something that's really nice to watch out for. And yeah. So let's go back here. So just to clarify, this A that we're talking about here, that is our semi-major axis. So it's basically this length here. That is going to be our A. And there's one more thing, which is these foci, right? These focuses. If you have a point on this orbit, the length of the length between your that point and the 2 foci is going to always be equal to 2A. So that's also something really nice to keep in handy. Remember conservation of angular momentum, and we have the energy equation that was just shown here. And so now we can move on to Kepler's laws. So this is a simplified form of Kepler's 3 laws that I'm going to talk about in a moment. But we can see here the 3 laws of planetary motion, and we can move straight into it. So just a little bit of history. Remember that Kepler came before Newton, so Newton actually mainly expanded on Kepler's ideas. So Kepler's first law was that planets have an elliptical orbit with a focus at the sun or the star, or whatever this body is going to be called. I'm going to keep on referring to it as a star, right? So the closest point is a perihelion. I hope I'm pronouncing that correctly. And so that's here. So that's the closest point in the orbit. Furthest point is the aphelion. So that's here. Remember, this is the farthest area. So remember that the gravitational force is proportional to 1 over r squared. This is the equation that's associated with it. You don't need to know this for the F equals ma competition. This is eccentricity. Doesn't matter. You don't need to mind this. Basically, eccentricity is based on this. You don't need to mind it. It's like the foci to the middle. Basic thing is the only possible orbits are going to be circular or elliptical for our cases. For other weird ones, we get parabolas and hyperbolas, but those don't matter right now. Second law, remember that a line connecting the sun to the planet, if a line is connected to this from the sun to the planet, so like this, it'll create equal areas during equal time periods. So if we look at this part, this area is going to be the same area as this, and both of these were created during the same time. And so this is based on angular momentum. If you zoom in really closely, you can see that there's a proof over here, but the basis of it is that the derivative of our area by time is going to be constant. It's this L over 2m, right? And so this is also why orbits lie on a plane. The L vector, so our angular momentum vector, is always perpendicular to our radius and velocity vectors. So the radius and velocity vectors always lie on the same plane. Because this law is based on the conservation of angular momentum, this law does not adhere to the proportionality of gravitational force to the radius. So basically what that big jumble meant was that it isn't reliant on the fact that the gravitational force has to be directly proportional to 1 over r squared. And this is something that Newton proved with the first and third Kepler laws. He found this correlation. The big thing is that the second law is not dependent on that proportion. And this is seen in one of the questions that we'll see later. So let's get back into the slideshow. So Kepler's third and final law, I hope, his third law is that the square of the period is directly proportional to the cube of the semi-major axis. And we talked about what the semi-major axis was. Hopefully you still remember. So this is the proof that's associated with it. You can read through it. The basics of this is that this t squared is equal to, this is a constant. So that means that the t squared is always directly proportional to r cubed, or our semi-major axis cubed, right? So for center of mass problems where we might have maybe the sun and the planet around, the star and the planet around it, both orbiting some center of mass, or we just have maybe a lot of planets orbiting some center, remember that for those center of mass problems, both objects will have the same orbital period. So this star will, if you can see, this star will have the same orbital period as this planet here. And so remember that the center of this is going to be known as the barycenter. So this point here is known as the barycenter. And so every object around it is going to be orbiting have the same orbital period. Sorry. So just some extra stuff. We have Shell theorem and Vis-Viva equations. So these aren't tested too much. It's just nice to have this knowledge, and I'm pretty sure Shell theorem is tested a little bit more in the future. But Shell theorem, basically any object inside a hollow sphere has a net force of 0, and we can see the proof here, or at least the explanation here. If you want a full proof, you can search it up. It's very complicated and very calculus-based, and I'm not going to explain it. We have the Vis-Viva equation, which is used for quote-unquote Keplerian orbits. So this is v squared equals gm. This is sometimes denoted as, with the mu symbol, gm times 2 over r minus 1 over a. And this is also a way for us to find our orbital velocity. If we just use this logic, what is this? V squared equals gm. And this is also a really easy way to remember the equation. So gm times 2 over r minus 1 over a, right? If we have a circular orbit, that means that a is equal to r in a circular orbit, right? So we have v squared is equal to gm times 2 over r minus 1 over r, right? And this is, remember, this is for circular orbits, right? So that means that v squared is equal to gm, and remember 2 minus 1 is 1. 1 divided by r is 1 over r, so gm over r. If we just take the square root of both of these, we get that our orbital velocity is going to be the square root of gm over r. And this is for a circular orbit, remember. So that's how this equation works. That's the Vis-Viva equation for you. And it's kind of handy whenever you have some weird velocity questions, which we'll see in a moment. But let's go back to our scene. I'm pretty sure that's it for the slideshow. Yep. So let's go to our questions. So consider the two orbits around the sun shown below. Orbit P is circular with radius r. Orbit Q is elliptical such that the furthest point B is between 2r and 3r, and the nearest point A is between r over 3 and r over 2. Consider the magnitudes of the velocity of the circular orbit VC, the velocity of the comet in elliptical orbit, so this orbit, at the furthest point VB, and velocity of comet nearest point VA, so here. Which of the following rankings is correct? And they give us these options, right? So we can use some process of elimination, right? So First thing, let's just kind of determine what's going on in this problem, right? So we have a star, right? We have a star, a very beautiful star, as you can see. We have a circular orbit, which we're going to say perfectly aligns because I know what I'm doing. Circular orbit. And then we have an elliptical orbit, right? So something that probably looks a little bit like this, right? So let's look at this, right? So we're told this is VC. Haha. This is VB, right? And this is VA, right? We know that the radius here is between r over 2 and r over 3, right? And we know that the radius here is between 3r and 2r. And this radius here is going to be r, right? So let's look at these rankings, right? Remember our conservation of angular momentum. So the further away, the greater the radius, so the further away an object is from the star, its velocity is going to be less, right? So for this object, so we know that the velocity here, which is the closest, so VA is going to be greater than VC, which is greater than VB. So let's look at some of the options first, right? So let's first look. We see that for our first option, we see that VB is greater than VC. So that means that A is definitely wrong. 2VC is greater than VB, which is greater than VA. VA is smaller than VB. VA is greater than VB, which means that B is also wrong. C of 10VB is greater than VA, which is greater than VC. We're not going to touch on that, but this part looks about right. VC is greater than VA, that's already wrong. And we have 2VA is greater than square root of 2VB, which is greater than VC. So our only possible options are C and E, right? So let's go back to here. And let's denote some stuff, right? So let's say that big R is going to represent... actually, no, that's not a good idea. Okay, so let's first look at... the relationship between VB and VA, right? That's our big problem for C, because that's like 10 VB and VA. So, with our whole thing about angular momentum, we know that at this point, VA is going to be at the very least 4 times greater than VB, right? Because we if this length is r over 2 and this length is 2r, that means that VA is 4 times greater than VB, right? And the greatest is going to be, this is where our radius is r cubed, and our furthest radius is going to be 3r, right? And that's going to give us 9 VB. So the largest value that VA can be is 9 VB, right? So that means that C is already correct, right? So we can say that C is correct since this is 10 VB. And for the other option, option E, that bases on the fact that bases VA and VB, right? And so that's something more based on our conservation of our energy equations that we showed before. And since we've already determined that option C is correct, since we're probably going to be on a time crunch, it would be better to just move on. So let's move on to the second problem. We've already determined that this one is option C. So let's read this out. So a spherical cloud of dust in space has a uniform density of rho and a radius r, right? The gravitational acceleration of free fall at the surface of the cloud due to mass is g naught, right? So a process occurs that causes the cloud to suddenly grow to a radius of 2r while maintaining a uniform but not constant density. So the density changes, radius changes. Gravitational acceleration of free fall at the point r naught, which was the original radius, due to the mass of the cloud, is now something else. So when I originally looked at this problem, I'm like, oh, this is easy. It's not based on density, right? So we can just say this, and then we can say it's g over 4. That is not correct, because remember, we're dropping from the original point. So our mass is going to be much smaller from that point, right? So let's go straight back to our scene. So we have a set rho, and we have a set r, right? So heat expansion causes our radius to grow by 2 times, right? Remember that our density or our mass is going to be constant, right? And since our radius grows by 2 times, our radius is directly proportional. Our volume is going to be directly proportional to our radius cubed, right? And this is just a basic understanding, right? If you take, this is basically square cube law. If you increase this length by 2 times, the volume will change by 8 times and the area will change by 4, right? This is just a basic square cube law. So, our volume, this is not velocity, is directly proportional to our cubed, which means that our volume grows by 8 times, right? Which means that our density, since our mass stays constant, our density is going to be equal to our original mass divided by 8 times its volume, its original volume, which means that it's going to be equal to 1/8 of our original density, right? So that means that if our radius grows, right, and we drop from this same point, sorry. So yeah, okay. So what this means is even though we're dropping from the same radius, right? So our equation, remember, our equation is going to be gm over r squared, right? And so even though our r won't change, our mass is going to be 1/8 of what it originally was, right? Because it's going to be the same area but with 1/8 the density, right? So that means that our final acceleration is going to be 1/8 of our original acceleration. And if we look back on our on our homework, we can see that that's going to give us c, which is our g0 over 8. All right, so next one is simple, right? Kepler's laws, those are Kepler's laws. We just talked about those. Which of these laws would remain true if the force of gravity were proportional to 1/r cubed instead of 1/r squared? We talked about this. I hinted at it a lot. Only our second law is going to stay the same. Remember that it's the only one dependent on angular momentum instead of the gravitational force. So only the second law will be will still remain true. The other ones will be changed. So next one, a planet orbits around a star S shown in the figure. The semi-major axis is A. Perigee, which is the shortest distance, is 0.5a, right? When the planet passes through point P, it has a speed v1. What is the speed v2 when it passes the perigee? And it's based on v1. So let's go back to the drawing board. So this is going to be based on our little vis-viva equation, right? Which is gm. So our v squared is going to be gm times 2/r minus 1/a, right? So now our big thing is, what is our r at our different points, right? So we have a star here, and we have an ellipse, right? This is very much drawn to scale. And so remember that this is going to be 0.5 of a. We have some distance, which is denoted as sp in the equation, right? Sp. I'm going to denote this as d1, right? And so this is also going to be 0.5a, and remember that this is going to be a, right? So the whole hint that, so given a point, if it's at the distance between the two foci will always be the same, which is 2a. So how this is going to work, right? We're going to find this length, and we're going to find this length, and this is always going to be equal to 2a, right? So that means that if we go back to this, how did I do this originally? So d1 plus this d1 plus this length, right? This length, we can use a Pythagorean theorem, right? We have I believe this is a, and we have d1, so plus square root of d1 squared plus a squared, right? This is going to be equal to 2a, right? This was our equation before. So this means that this length, right? So d1 squared plus a squared is going to be equal to 2a minus d1 and all this squared, right? So that means that d1 squared plus a squared, remember we have binomial expansion, so this is going to be 4a squared, we have FOIL, minus 4a d1 plus d1 squared, right? So we can start shifting stuff around. We can cancel these out. We can subtract this on this side and just get 3 here. So 3a squared is going to be equal to 4a d1, and we can do this by moving this to this side, right? So that means that we can divide 4a on both sides. So d1 is going to be equal to 3 over 4a, right? So this simplifies things a lot, and I'm just going to move this over here, shrink this just a tiny bit. Nope, that is not the shrink button. This is the shrink button. Okay, so now we have d1 is equal to 3 over 4a, right? So we can just plug this straight back into our vis viva equation and just find the ratio, right? So v2 squared over v1 squared is going to be equal to, and this is going to be our ratio, remember? So this is going to be, we can just eliminate gm because that's going to be repetitive. So 2 over r minus 1 over a, right? Our r for this case, remember, for our v2, that's going to be 1 over 2a, right? 1 over 2a minus 1 over a, right? Divided by 2 over, and we just said that d1 for v1 is 3 over 4a minus 1 over a, right? And this is going to give us a ratio. We can just eliminate these and like actually do the math. So 4 minus 1 over 8 over 3 minus 1. And this bottom one, so this is going to be 3 over 5 over 3. And so that's going to give us 9 over 5, right? That's just simple arithmetic, or whatever it's called, fraction stuff. Anyways, we have this part, which means that our v2 squared is going to be equal to 9 over 5 times v1 squared, right? That's what ratios are. And so that means that our v2 is going to be equal to 3 over the square root of 5 times v1. And if we look back on our slideshow, not our slideshow, our assignment, we can see that that's going to give us option A, which is v2 is equal to 3 over square root of 5 times v1, right? So that was quite a bit more writing than I expected, but it wasn't too bad, right? Okay, next one. There's a calculus way of solving this. I'm not going to do that one. So, a satellite is following an elliptical orbit around Earth. Engines are capable of one-time impulse of a fixed magnitude. In order to maximize the energy of the satellite, the impulse should be one of these. So, you can do common sense or you can do the math. You can probably solve it with common sense, but I'm too lazy to do it the common sense way, so I'm going to write this out, right? So, our change in energy, right? Remember that our impulse is going to be mdv, right? So, our change in energy is going to be equal to 1 over 2 m times v, like the original v, plus the change in v squared minus 1 over 2 mv naught squared, right? And this is our original speed. And so, if we were to write this out, that means that our change in energy would be equal to what is essentially 1 over 2 m times, remember, expansion, so this is v naught squared plus 2 dv dot v naught dot product, remember, plus delta v squared, right, minus v naught squared, right? And so I think this is correct. And so what we can say here is this is 1 over 2m times 2 dv dot v. And remember, we have our little, if you know dot product is where a dot b is going to be equal to length of a times length of b cosine theta. And this is a little bit more complicated than needed. So that means that we have 2 times r dv times r v naught cosine theta plus v squared, right? And so first thing, to maximize this, we need to have our impulse directed along the satellite's velocity, right? Because that means that our angle would be equal to 0, where our cosine theta would be equal to 1, which is our maximum value, right? So we know that that's going to eliminate C, D, and E. And finally, we know that this is going to be maximized when V naught is largest. And V naught is going to be the largest at the closest point, which means it's going to be at its perigee where it's the largest. So if we look back at our homework, that's going to give us option A, where it's directed along the satellite's velocity and applied when the satellite is at its perigee. That explanation might have been incorrect. I might have gotten something wrong. But the main idea is, if you just think about it, at its closest point, it's going to have the maximum highest speed, and you have to direct it along the satellite's velocity, right? So, final question. This is an easy one. A satellite is in a circular orbit around Earth. Over a long period of time, the effects of air resistance, blah, 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 decrease the satellite's total energy by 1 joule. The kinetic energy of the satellite increases, decreases, remains unchanged. So, we just talked about this, where our energy is going to be negative of our kinetic energy. So, if we just look back here, since it decreases by 1 joule, that means that the total kinetic energy increases by 1 joule. And so that's going to give us option A, and that's going to end our homework right there. So thank you so much for listening. Thank you so much for watching. I hope you have a good day, and yeah, have fun learning physics, and I'll see you next week.